Hello everyone and welcome to another Stat 437 lecture video. In today's video, we're going to be talking about some basic notation that we use for longitudinal data analysis and talk about some of the jargon or the words that we're going to be using throughout the term to describe longitudinal data that'll keep coming up. And so we'll try to just get somewhat familiar with all of this. So with that, I will open up my whiteboard here, and we can begin talking about sort of the basic notation. So as a brief review of notation that's standard across your statistics courses generally, and that we'll continue with here, we're going to typically use capital letters as random variables and then lowercase letters as observations of those random variables. So we might have that, say, capital Y is a random variable, and we might be able to say that Y equals lowercase y, right, when we, as a realization. And so this should be standard notation that you see throughout sort of all of your stats courses. That's quite familiar to you. And we'll continue with that here. As another point of information, again, this should be standard, but we'll typically use Greek letters to denote parameters of a model, right? So we'll use something like theta or beta or alpha, and these will typically be parameters. And that should be obvious from the context that we're working in, sort of what they represent. So in terms of longitudinal data specifically, the one piece of information that we have that sort of distinguishes it from what we might be used to looking at is that we have indexing over not just the subjects in a study, but also indexing over the different time points that are involved in this study. So what I mean by this is that you would normally think about taking, say, some index I, right? And we'd let I go from 1 up to n, and n is the number of observations in our study. And then typically you would have something like y1, y2, up to yn, right? And here the problem is that we don't just have a single observation for every individual. Instead, for each individual, so for y, or for individual I, say, we're going to have, say, k or ki observations. So we have ki observations, right? And ki is going to depend on the study. In the TLC trial data that we've looked at, ki would be 4 for all individuals, but we could think about ki being any other constant value across the study. We could also think about it depending on the individual. So maybe some people got 10 measurements and some people got 5, right? And so we have these ki observations. And so the way that we're going to do this is using a double indexing approach here. So we're going to use the notation of y, I, j. And this is going to be the outcome. And we're talking about the outcome because we're using the letter y, and y is going to represent outcomes here. And it's for individual I. And so this should be standard from your other stats courses. We use I to index over individual, and so I runs from 1 to n. And we're going to say at measurement j. Okay, and so j here is going to run from 1 up to ki, and we have I running from 1 up to n. Okay, and so we're just sort of listing through the different time points here, right? So we're assuming implicitly with this notation that we take measurements at some set of times, say t1, t2, up to tki, and then we just associate each measurement with this being sort of the TJ observations, right? And so again, if you're looking at 4, then we knew that, say, T1 was equal to 0, T2 was 1, T3 is equal to, I think, 4, and then T4 was 6, measured in weeks, right? And so we can have these different values for them, but in any event, we just sort of enumerate through the different outcomes. And so that gives us our the outcomes from our study. And so then we can do a similar thing if we want to look at explanatory covariates. And so instead of using Yij, we're going to use Xijk, right? Xijk. And the idea here is that the I and the j are going to be the same as above, right? So we index over individuals I at time points j. And so then what's this k that we have going on here? Well, the k is just going to enumerate the different explanatory factors that we might care about, right? And so you could think if we're looking at, say, age, sex, height, treatment, all of these are going to be different factors that we might care about. And so then these would be Xij1, Xij2, Xij3, Xij4, and so on. Now, the other piece to note here is that some factors that you measure aren't going to change over time, right? And so you can think about the treatment status, for instance, right? If you're in a study where you're assigned to be in the placebo group, then you're going to be in the placebo group for the entire duration of the study. And so what we would have there is that Xij4 is going to be equal to the same value, sort of, no matter which j you're at. So Xij4 is constant. Now, you could think about a variate like age, right? And age is going to potentially change over time. Now, maybe age measures the age at the baseline, at which point it's time invariant, it's stationary. But you could also think about this as being updated at each time point, right? If you're measuring over years, or perhaps you're taking longitudinal measurements every 5 years, then this age factor is going to update over time. We're going to want to be careful when we have these time-varying covariates. And so if we use the term covariate, what we're really talking about is a variable that changes over time that we're going to use to explain our outcome. So with these covariates, we have to be quite careful about how we include them in the model, and we'll talk a little bit more about that in the future. But needless to say, we can still sort of think about Xijk even if they're not changing over time, and it's just going to be the case that Xi1k is the same as Xi2k, and so forth, right? So both Yij, we can say that our goal in this longitudinal modeling is going to be something like we want to explain Yij using sort of Xijk, right? And we're going to want to do this for all ijk. Now, this notation is quite cumbersome. I'll be the first to admit. And so what we will often do is shorten this to be talking about vectors, right? So the first sort of most obvious vector to use is to say, take Xij, and we're going to define this as a vector now, and this is going to be equal to Xij1 up to, and let's say that that k ranges from 1 to L. Then we can take Xij to be the vector Xij1 up to Xijl. So it's just a vector that contains all of the explanatory variates at time point j, right? So then now we're going to be able to sort of just talk about Yij and Xij. And so Xij is just all explanatory factors measured at time j. Yij is the outcome measured at time j. Okay, now we can do a similar thing talking about the outcomes. If we just care about one individual, we could write Yi as a vector which includes yi1, yi2, up to yi, and then k sub I here. Okay, and so this is going to be a vector of just the outcomes. And now each individual has a vector outcome, and we're thinking about it as sort of as multivariate data. We can do a similar thing with xij, except we see that xij is already a vector, and so instead of doing a vector, it makes sense to think about stacking this into a matrix, right? So we could talk about xi as being the matrix where we take xi1, xi2, and so on, up to xi ki here. And should have write this. And so this is going to be a matrix where each row represents a time point and each column represents a specific factor of xik. And so both of these are sort of natural ways of extending this notation, and we're going to use both forms, both the individual scalar terms, as well as these sort of vectorized and matrix versions. Now, one thing that I will say is that when we're dealing with vectors and matrices, it can be somewhat confusing to recall the dimensionality of it. And so anytime that I'm working through a proof of anything or a derivation, I'll try to specify what size these matrices are, right? And so we're thinking about yi as typically we would be thinking about it as a row vector, but we can interchange row and column vectors just through the use of a transpose. And so sometimes we might think about it as a column vector versus a row vector. And then we can think about the fact that this matrix is going to have ki by L dimensionality here, right? There are ki rows, one for each time point, L columns. Now, sometimes we're also going to need to be thinking about xi transpose, right, which we would just denote with the tick up there, and then that's going to be each factor gets its own row and measured over time. And so either way, we can sort of interchange them as is necessary for the problem at hand. So that covers most of our notation, but there's a few other pieces that we should be discussing here. So I've already indicated that we have these time points, which we would denote t1, t2, up to tki, right? So these represents the time points for individual I. Now, if all individuals had the same times measured, or so had measurements taken at the same times, then we call this design balanced, and we do not need this subscript I anymore. So what I'm saying here is that if for all I, ki is equal to some constant k, right, then we would have the fact that all individuals have the same k measurements taken, and we say that the design is balanced. Now, we're going to talk a lot about balanced longitudinal data. So the TLC study, every individual in that study had measurements taken at weeks 0, 1, 4, and 6, and so it was balanced. Balanced data are quite a lot nicer to deal with. Now, we're not always going to have them in the real world. We're going to sometimes have studies where individuals have different numbers of measurements, as previously discussed, and we're also sometimes going to have studies where the time points that were taken don't necessarily line up. And so we're going to have to be careful about sort of those distinctions that might arise. But on the whole, these balanced data are a special case where ki is equal to k, and they're going to be the case that we actually focus a lot of our attention on because they're nice to deal with and they're a good way of presenting the models. So unless we're sort of talking more generally, you can always fall back on this thinking about balanced data, and that might help simplify the process as we work through the course. Now, that is sort of all of the major notation that we're going to need that's not model specific. So just to quickly recap, we have y's as being outcomes, we have x's as being explanatory factors, and we have t's being time points, and then these are subscript subscripted as necessary to include sort of all of the values that we could be looking at. And so we would have Tij's, and then, if it's balanced, that's specified, or that simplifies just down to Tj. Now, we can also think about some additional language that's going to come up throughout this term. And so as new terms arise and as new notation arises for specific models that we're talking about, I'll do my best to introduce those and describe them as we go. But a few pieces that I've already been using that we probably should clarify is, well, the first that comes to mind is I'm going to be talking about the individuals in a data set quite often. Now, I'm going to talk about individuals because most of the data that we're dealing with happen to be medically relevant or biostatistics type data. And so there we would have a sample of individuals, and each individual is going to have one of those indexes I. But we could also talk about individuals even if it's not people that we're talking about, right? So I showed an example of podcast data at the beginning, and there individuals would refer to individual podcasts, but still we're going to refer to them as individuals. Now, I think that as a general rule, there shouldn't be too much confusion about sort of the way we're discussing these data. But of course, if I'm ever using language that you felt I haven't introduced or that I have forgotten to bring up, please let me know, and I'll do my best to describe what that is exactly. But hopefully as we go, you'll just become familiar using all of this language sort of as you need. Now, the last point that I want to make today is just on this idea of time and how we're going to refer to time sort of more broadly, right? So in the TLC study, right, we had time 1 equals 0, time 2 equals 1, time 3 equals 4, and time 4 equals 6. And this was true for all individuals. Now, we've already briefly talked about the difference between balanced and unbalanced data, but I also want to just discuss the fact that there's sort of countless ways that we could talk about the time in a study. So here we're talking about a very discrete time scale where we're measuring the number of weeks, right? And so that's going to be a sort of discretized version of time. But we could also think about a continuous time, right? And so some timescales are going to be more natural to think about continuously than others, but we could even think about this as being continuous weeks and just, let us have like 0.25 of a week, and sort of depends on how granular we want to be with it. We can also think about time, so if we're talking discrete versus continuous, we can also think about it as being time sort of relative to the calendar, right? So we can think about dates, which we saw in the podcast data. We could also think about changes in time, or time since a baseline, right? So time since baseline. And what I mean by this is that we might have a study where people enroll in the study at different periods in time, right? So if you're thinking about this as sort of some timeline here, right? And so maybe we have the first individual who enrolls at what is actually time equals 0, and we sort of follow them up till time equals 5, say, okay? And so they're in this duration of the study for a period of 5 time points, right? You might have a second individual who doesn't enroll in the study until, I guess that would be about time equals 2.5, let's say, why not? And maybe we follow this person up till t equals 7.5. Right? And so there's sort of two ways that we can think about this setting. We can either talk about this time scale down here, which would be equivalent to sort of calendar time, where everything is based off of this time 0, or we could shift these people back in time and talk about it as where now here they're both measuring t equals 0 to 5, where the time is measuring the change from the baseline, right? And so either one of those might be appropriate depending on the question that you're looking at. If what you're expecting is that you give someone treatment when they enter the study, and then sometime after they've received this treatment, you expect something to happen, right? Then it might just make sense how long have they been in the study for. If we're talking about, say, the sales data, where there might be a seasonal component, it's not going to make sense to talk about these on different timescales here. So we can have choice over the timescale that we want to use, and that's really going to be up to the question at hand. So I think that really that covers everything to get our handle on the mathematical notation that we're using and some of the technical jargon that's going to come along with that. I hope that all makes sense, and I hope that you'll feel comfortable working with vectors and matrices and that type of thing. If anything didn't make sense, as always, please ask whatever questions you might have, and I will see you in the next lecture video.